Good evening. I'm Spot On Weather meteorologist Matthew Euler, and we are now moving into video number 8 tonight, and we're going to cover analyzing vertical air motions in video number 8. A couple images here on the title slide of tonight's training. The image on the left is showing you how, again, this is kind of a carry-on topic from the last video training session. But how everything is connected three-dimensionally. These images show it on the title slide. You can see the image on the left. We have surface highs and surface low pressure. We have air that's either rising or sinking. Above surface high pressure, you have upper level convergence or the accumulation of mass aloft. Above the area of lower pressure, surface low pressure, you have divergence aloft. Image on the right shows, again, upward and downward vertical motions. These are so very important. What's interesting is vertical air motion is so small, but yet it is so very important as far as our sensible weather here at the Earth's surface. So tonight we're going to take a little bit more in-depth look at something known as vorticity and vorticity advection. We're going to look at temperature advection, and we're going to look at the two and combining them. Temperature advection, those change in temperatures over a horizontal distance, and the vorticity advection, which has to do with indications of upward and downward vertical air motions. So let's kick things off tonight, and we'll begin by talking about vertical motions in general. The evaluation of synoptic scale vertical motion fields are of primary importance in analyzing and forecasting synoptic scale weather. Now, when I say the word synoptic scale weather, again, just as some examples of that would include frontal systems, cold fronts, warm fronts, stationary fronts, occluded fronts, low and high pressure systems. Synoptic scale is something that's going to happen over hundreds of miles. And so we deal with a lot of synoptic scale weather systems in the wintertime across the United States, especially when you have these areas of low pressures and these storms that travel great distances from coast to coast, from the west to the east coast, or perhaps they develop in the Gulf of Mexico and come up the east coast. But these are systems that cover quite a large area of real estate, and they last for days on end. With vertical motions, and I mentioned this in the last training, that's why this is kind of a continuation of the last training video. We talked a little bit about mass continuity, and simply put, mass continuity basically states that mass can be neither created nor destroyed, and mass is going to be added in certain areas and subtracted away from other areas. And whenever you have this removal of mass or this gain of mass in different areas of the atmosphere, that mass must be redistributed. You're going to have the same quantity of mass. That's not going to change. However, that where the gains in the mass are and where the losses of mass are is going to change dependent on whether you have surface high, surface low pressure, upper level divergence, or upper level convergence. So the equation for mass continuity, what that does is it links the divergence and the convergence of the horizontal wind to lifting or sinking, that chimney and damper effect, which we have covered in previous videos. So the mass continuity states that mass must be conserved, as I just mentioned, and this results in removal and addition of mass and ultimately a redistribution of mass. The quantity of mass again remains the same, all right? It's just redistributed throughout the atmosphere. There may be a gain in one area and a loss in another area. The actual horizontal wind direction and speed cannot be measured with enough accuracy to allow direct calculations of the resulting vertical wind. In other words, the horizontal winds that blow across the Earth's surface, those are not enough to allow direct calculations. We cannot use that wind that's happening on the Earth's surface. We cannot use that wind to accurately depict the resulting vertical wind. So we have other methods we can use to determine whether the air is rising or whether the air is sinking. These alternative indirect vertical motion methods must be developed, which may be partially or totally independent of the actual wind. And two of the most popular indirect methods And we're going to talk a little bit about the omega equation. And we're also, for sake of simplicity, I'm going to tie in the omega equation with various parameters of the atmosphere. And you'll see that on a chart towards the end of this training. The Q vector methods we're going to leave out for the sake of simplicity that are derived from that quasi-geostrophic wind relationship. So we won't really worry about that. My main focus is on vorticity changes and temperature changes and how these two tie into vertical air motions in tonight's training. And we look at that through what's known as the omega equation. First things first, and just bear with me as I go through a few of these slides, and we'll have some graphs and we'll be able to more thoroughly look into these different statements. Just bear with me here as we go through some of this terminology. First things first, quasi-geostrophic theory and vertical motion. There are some main limitations of what's known as a quasi-geostrophic theory. First of all, it provides only a first inference of where and why vertical motion may be occurring in the atmosphere. The second limitation is it should not be applied in the tropics, where the synoptic scale flow is more ageostrophic in nature. We really don't have a lot of synoptic scale weather systems in the deep tropics. And the main reason is because it's a barotropic environment where we do not have any kind of temperature changes. Additionally, the jet stream, which is that upper level source of energy, is well to the north of this particular area on the Earth, well north of the tropics. The only example I can think of a synoptic scale type of weather system in the tropics would actually be a hurricane. That would be an example because it impacts a very wide area and it covers a very expansive area, as well as its impacts could cover more than one day. Tropical systems can last for quite some time. But that would be the only example of a synoptic scale system in the tropics would be a hurricane. Outside of that, the flow is very weak. There's very little change in temperature in the tropics. So we just don't have anything major going on as far as synoptic scale flow there. Additionally, the third limitation is the quasi-geostrophic theory should be used with great caution in active weather regions where you have that divergence is large and non-hydrostatic conditions may exist. Another limitation here, vertical motion produced by topography. When I talk about topography, I'm talking about mountainous terrain. As we're all aware, on the Earth's surface, the Earth is not completely flat. The land masses will rise in elevation and they'll also fall into valleys, into lower elevations. So vertical motion produced by topography. What happens is the wind blows up against a mountain slope, such as the Rockies. It cannot blow through the mountain range. It's forced to go up and over. There's a lot of friction involved. And just remember, friction occurs because the wind is blowing against solid objects, and those solid objects tend to slow the wind speed down. Also, vertical motion produced by latent heating. This is a common concept. When I say latent, I want you to think of hidden. Can't really see this type of latent heating, but it's a very important process in the atmosphere, especially during the summertime when you get extremely warm and humid air masses that are very unstable and they want to rise. That air wants to rise in the summertime. You get strong heating from the sun, and it results in these convective air currents where in the process of convection where initially the sun heats the Earth's surface. It basically evaporates the liquid on the Earth's surface. That then becomes a water vapor. It rises, it cools, and eventually it condenses back out from a vapor to a liquid in the process of condensation. And what happens is it releases heat to the surrounding air. Through the process of condensation, heat is released to the surrounding atmosphere as an air parcel rises. Evaporative cooling is another topic. Radiational heating and cooling in small-scale processes will not be represented by the quasi-geostrophic theory and the omega equation. So any of these more smaller-scale effects, topography, latent heating, evaporative cooling, radiational heating and cooling in small-scale, stuff like that will not be properly represented. Omega, and I wanted to break this down. I took a good look at this. This is right from the source, from NOAA. But omega is a term that is used to describe vertical air motion. That's all it is. It takes into account the vorticity, which we're going to get into. Vorticity is simply the spin of the air parcel, and temperature advection, or the changes in the horizontal of temperature, in determining whether air is rising or sinking vertically. That's all omega is. I added that on because I felt like that was very important. When I say omega equation, when I use that word omega, that's all I'm talking about. I'm describing the vertical air motion, taking into account two main things, vorticity and temperature advection. Right. So this is an example of the classical omega equation. And I'm not going to get into any of the calculations. We're not going to do any math problems. But I'm going to use this equation, use these terms that are listed, terms 1, term 2, term 3, and we're going to talk about what each of these represents and how that plays into rising or sinking air motion in the atmosphere. So regions of synoptic scale vertical motion can be estimated by the omega equation. This is represented below in this particular equation by a relationship between vorticity advection and temperature advection. Advection is just simply the change in a property of the atmosphere in the horizontal. It's a change in the horizontal advection. So let's go ahead and break down the classical omega equation. The first thing we want to go through is what each term represents. So that Vm, the initials Vm out in front of the equal sign, that is our term 1. And that Vm stands for vertical motion. So ultimately what we're trying to do is determine the vertical motion. We're trying to determine whether that vertical motion is causing rising air or the vertical motion is going to result in sinking air. So term 1 is vertical motion, the Vm. Lifting is going to occur. So we're going to have rising air motion when the Vm is positive. When we have the vertical motion positive, that's going to indicate the upper level divergence. Okay? When you have upper level divergence, you have the removal of mass aloft. And as that mass is removed aloft, air comes from beneath it and rises in the vertical to replace the mass that's lost. It's going to indicate convergence in the lower troposphere. If we have upper level divergence, we have low level convergence beneath that. We talked a little bit about that level of non-divergence, the middle part of the atmosphere, where we have the change from convergence to divergence. So bottom line here, term 1 again is Vm represents vertical motion. Sinking air is going to occur when term 1 is negative. So if we have a negative sign, if we had a value in, let's say we had a value for Vm and it was a negative sign in front of it, that would mean that sinking air is occurring. Whenever we have sinking vertical air motion, that results in nice weather. Okay, that's going to indicate convergence in the upper troposphere. So we're having air streams come together in the upper troposphere. That's adding mass to the air column as they meet, and then the air sinks through a great vertical depth of the atmosphere until it reaches the ground. Once that sinking air reaches the ground, it spreads out. It spreads out, and that results in the lower troposphere divergence, the spreading apart of air streams, right? Spreading apart. All right. Term 2 in this classical omega equation. All right. Term 2 represents the change in absolute vorticity advection with the change in height. So you see the triangle, and then you see that strange looking symbol there, the N, and then represent a little G next to it, and advection, the word advection, over the triangle Z, delta Z. Z represents height, okay? So we have term 2 representing the change in absolute vorticity advection with a change in height. Now, we talked a little bit about this already. PVA stands for positive vorticity advection, and NVA stands for negative vorticity advection. So if term 2 is positive, that means that we have positive vorticity advection increasing with height. If term 2 is negative, if there's a value, there's a number, and there's a negative sign out in front of it. If that term 2 is negative, that means we have negative vorticity advection increasing with height. So PVA is generally associated with rising air motion, and NVA is associated with sinking air motion. And then finally, term 3 of the classical omega equation. You see that capital T and then the capital AdV? That represents temperature advection. We're just abbreviating it. So term 3 is temperature advection in the lower troposphere. So if you have warm advection, temperature advection can either be warm or cold. When I have warm air advection, I'm having warmer air move into my area. Temperatures are getting warmer. If I have cold air advection, colder air is moving into the area. My temperatures are getting colder. So if term 3 is positive, that means I have warm advection. If term 3, the temperature advection is negative, I have cold advection. Right? Now what happens if both terms 2 and 3 have the same signs? So term 2 and term 3 have the same sign. Let's say both are positive or both are negative. If both of them are positive, this is going to enhance the magnitude of lifting. And it's going to result in term 1, that VM, the vertical motion, being strongly positive. So if I have positive vorticity advection and I have warm air advection, or a positive value in term 3, that's going to result in a positive vertical motion, right? That is going to enhance the lifting. So the air is rising in that case. If I have both terms 2 and 3 of the classic omega equation, both terms 2 and 3, vorticity advection and temperature advection, are negative, this is going to enhance the magnitude of sinking air motion. So I hope that makes sense. All right, we can have like signs, either positive or negative in terms 2 and terms 3. Okay. However, you can also have a case where terms 2, the vorticity advection, and term 3, the temperature advection, are opposite signs. All right, so let's say term 2 is positive and term 3 is negative. Vorticity advection is positive, temperature advection is negative. Okay. This may tend to offset basically one term is going to offset the other. And this is going to reduce the magnitude of lifting or sinking in term 1. The vertical motion is going to be, basically they counteract each other. Vorticity advection and temperature advection, if they counteract and act against each other, then obviously your vertical motion, term 1, is not going to be as strong. Right? You may have a case where term 2 is positive, the vorticity advection is positive, term 3, the temperature advection is negative. This tends to offset and cancel each other, again, the two terms, and that's going to reduce that magnitude of lifting or sinking. In this case, if one's positive, let's say for vorticity advection, term 2 is positive, and temperature advection, term 3 is negative, and they're different signs, that term 1, your vertical motion, may be either positive or negative. And we would have to know more about what's going on in the atmosphere to really determine if the vertical motion is rising or sinking. Now, term 2, your vorticity advection may be negative, and term 3, the temperature advection, may be positive. And this will tend to offset, cancel one another as well, and again, reduce the magnitude of lifting or sinking of the air motion. And again, that term 1 vertical motion in that case may be either positive or negative. It may either be rising or sinking. So in this case, the dominant term, the one that's stronger, will determine whether the air rises or sinks. Whether we have air that rises producing stormy conditions, or whether we have air that sinks producing very nice clear skies. But because terms 2 and 3, that vorticity advection and temperature advection, may oppose one another, each term's influence on vertical motion will be evaluated separately. And that's generally where we're heading right now. We're going to take a look at a bunch of scenarios here. We're going to take a look at if I just have certain temperature advection and I don't have vorticity advection, or if I just have vorticity advection and don't have any temperature advection, or if I have opposite signs. We're going to take a look at that next. So if we were to look at evaluation of individual terms in the omega equation, let's just say we're going to evaluate term 2 from the equation, the vorticity advection term, which is noted here below. Right? We're not going to consider the temperature advection at all. Term 3 is out of the equation. Notice this? I only have term 1 vertical motion VM and term 2, the vorticity advection. All right, so if I have positive vorticity advection, so my term 2 is positive, that means my vertical motion is going to be upward. Okay? See that? If I have a positive vorticity advection, positive term 2, and that's going to result in a positive vertical motion term 1. What does PVA, or positive vorticity, indicate generally in the atmosphere? This indicates areas where there's divergence or spreading apart of air streams or air currents in the upper troposphere. Above that LND, the level of non-divergence. So above, in the upper levels of the atmosphere, you have spreading apart of air currents, you have a removal of mass aloft. And it also indicates you have low-level convergence. So at the ground, at the surface where we live, you have wind that's converging, air currents converging, and as these air currents meet, they got to go somewhere. So that results in rising air motion. That rising vertical air motion is going to replace the mass aloft that you're losing via divergence, and it's going to result in upward vertical motion. What does that mean when you have rising air motion in the atmosphere? That means you have a lowering of your height surfaces. The surface pressure is going to lower as well. If you had one of those home barometers, if you ever notice when an area of low pressure is moving in, you'll notice the needle on the barometer gets lower and lower. That's because we have an area of PVA moving into our area at about 18,000 feet. Between 10 and 18,000 feet, you have this area of PVA moving overhead. I'm going to show some excellent charts to end the training tonight, and I'll show you what these vorticity charts look like. You're also going to get with PVA unstable weather conditions, so you're going to have a lot of clouds with the rising air motion, a lot of precipitation for the most part. The image on the left-hand part of the image here shows the results of just positive vorticity advection, PVA. Again, think of the atmosphere as a three-dimensional fluid. We have to look at the surface, and we have to go all the way up to where that jet stream lives, up at 30,000 feet. 300 millibars. Right? So the image on the left shows a case where you have positive vorticity advection, PVA. The area at the surface represented by a counterclockwise circulation. The arrows are basically the wind is moving inward towards the center of the low pressure. As you go aloft, 700 millibars, the second level on the diagram on the left. 700 millibars, about 10,000 feet, you have an upper level trough. If you go all the way up, there's a level of non-divergence marked LND. You have low-level convergence beneath the LND, but then you start getting upper-level divergence at 18,000 feet and 30,000 feet above the LND. We have rising upper vertical air motion. Everything is stacked back with height towards the colder trough aloft. Okay. At 500 millibars with a low pressure at the surface, that's where you have your PVA. Do you notice the dark arrow for the diagram on the left, how it's pointing towards this PVA area out ahead of the upper level trough there at 500 millibars or 18,000 feet in the atmosphere? PVA is there. It's over your location. It's starting to interact with the surface low pressure system. That's going to result in intensification of that surface low, a stronger storm system. And then above that 500 millibar level, the left-hand portion of this image, you'll see 300 millibars at the jet stream level. We are in the upper level divergent quadrant of the jet max, which we covered extensively in the last training. The removal of mass aloft via both PVA at 18,000 feet or 500 millibars and the upper level divergent quadrant of a jet max at 300 millibars, 30,000 feet. We're simply looking only at positive vorticity advection in this case. Term 3 temperature advection is out, and it's going to result in upward vertical motion. Now let's look at negative vorticity advection alone. What does NVA, or negative vorticity advection, do for us? We're only considering terms 2 again. We're looking at terms 2, and we're looking at term 1, vertical motion, VM. If we have negative vorticity advection, it's going to result in a negative downward motion. Okay, so we have downward vertical motion with negative vorticity advection. What does this NVA indicate? It indicates areas where you have convergence in the upper atmosphere now. Okay? You have air that's coming together. The air currents are meeting. And as they meet in the upper levels of the atmosphere, they're adding mass. And then as they meet, the air is forced to sink down vertically. And as that air sinks, eventually it's going to hit the Earth's surface, which is horizontal, and spread out, resulting in low-level divergence below the LND. You're going to have downward vertical motion whenever you see an area of NVA on a weather chart overhead. You'll have an increase now of the constant pressure surfaces in the upper levels of the atmosphere. Your 700 to 500 millibar, it's going to expand and get taller. Surface pressures are going to rise as well. And then you possibly will have what's known as anti-cyclogenesis, or the strengthening of a surface high or the development of a surface high. Okay? And that is going to result this downward sinking air motion. I've said this before, but as air sinks in the atmosphere, it dries out, clears this. Basically, the drying out is going to dissipate the clouds, and it's going to result mainly in clear skies and nice conditions. Very stable atmosphere, stable, nice day. Let's take a look at the image on the right-hand portion of this image. Now we're going to talk about results of NVA, negative vorticity advection alone. So notice at the surface on the bottom right, I have divergence. Low-level divergence. That basically means as the dark arrows indicate downward motion, as soon as that air hits the Earth's surface, that air is going to spread out horizontally, resulting in that low-level divergence. Air is moving outward and away from the center of high pressure at the surface. Generally, that surface high is going to stack back towards warmer temperatures aloft and also towards an upper-level ridge aloft. If you notice at 700 millibars, 10,000 feet, we have a little ridge axis just to the northwest of the surface high. You have the level of non-divergence, once again, the mid-levels of the atmosphere. And then above that level of non-divergence, the air is actually converging. And with the converging air, we have an area of NVA at 500 millibars directly over that low-level divergence at the surface high. NVA, which indicates lowering vorticity values. And then you're also in the upper level convergent quadrant up at 300 millibars. Upper level convergent, air is converging at 300 millibars, 30,000 feet, with the jet axis, with those jet maxes, those high little pockets of wind energy. And it's also an area of NVA at 500 millibars or 18,000 feet. So bottom line here, NVA results in sinking air motion. What happens if we have neutral vorticity advection? So we have a case of positive vorticity advection. We have a case of negative vorticity advection. But there's also could be a case where term 2, the vorticity advection, is neutral. In other words, it doesn't have a sign. It's not positive or negative. In this case, vertical motion is going to be 0. So neutral vorticity advection is going to indicate areas where your vorticity lines and your height lines are parallel to each other. They do not cross. Vorticity values have reached either a maximum or minimum value, and the wind flow is too light. You could have a case where the wind flow is just simply too light and it doesn't really move the vorticity values. It really doesn't change the vorticity over time when the wind is really light. In this case, you get little or no convergence or divergence aloft. Okay? So the relationships between 500 millibar height contours and the vorticity isopleths, that's what we need to take a look at next. Okay? And I'm going to show you an example again at the end of the training on what a vorticity chart looks like. We'll get into explaining it a little bit more, what the different lines mean on it. We have something that's known as vorticity lobes. And I'm going to show you 2 types of vorticity lobes in the training. Vorticity lobes are simply areas in which vorticity, and when I say isopleths, all I mean is a line of equal value. Iso literally means equal, pleth means line. So a line of equal lines of some sort of value. That's what isopleth is. So when you have the vorticity lobes are areas in which vorticity isopleths are elongated. There's 2 types of vorticity lobes. There is what's known as advection lobes, and these lobes are aligned perpendicular to the wind flow. These indicate the possible existence of a shortwave, trough or ridge, at the 500 and or 700 millibar levels. This could be a minor or a major shortwave. These are the weather makers. This is what is associated with those areas of positive vorticity advection and negative vorticity advection. They're very critical. If you get the area PVA overhead at 5 and 700 millibars, there's a good chance your air is going to rise vertically. You're going to form clouds. You're going to get precipitation. You're going to get upper level divergence. If you get that area of negative vorticity advection on a weather chart on the 500 to 700 millibar levels, you're going to have sinking air motion. Most likely you're going to have nice, fair weather. So very important, these lobes. Here's an example of what it would look like in an advection vorticity lobe. This is associated with the weather makers. When you hear the weatherman on TV, the weather meteorologist on TV say, hey, we have upper air disturbance moving through, this is what they're referring to. The image on the left shows what these dashed lines, okay, and it also shows solid black lines, image on the left. The dashed lines represents equal lines of vorticity values. The solid lines indicate equal or constant height pressure surfaces. Okay. Whenever the dashed lines cross the solid black lines at any angle, that's going to result in vorticity advection. When the vorticity advection is neutral, the dashed vorticity lines are parallel to the dark solid height contour lines. So with neutral vorticity advection, there's no intersection of the dashed lines with the solid black lines. The vorticity lines are perfectly parallel to the height contour lines. The black solid line in this particular image indicates a advection vorticity lobe. All right. It's showing, and I made a comment at the bottom here of the slide, these advection vorticity lobes are mostly found at 500 millibars or 18,000 feet. They can also be found at the 10,000 foot level as well. All right. Another type of vorticity lobe is what's known as a shear lobe. And these are lobes aligned parallel to the wind flow, predominantly caused by speed shear. So you would find shear lobes in the vicinity of a jet stream, most likely, because there's a lot of movement, fast movement of wind speeds within that jet core. Shear lobes are very useful in locating those jet maximum. Those little pockets, those jet maxes of very fast-moving wind speeds are usually associated with the shear lobes. So here's an example. The dashed lines again represent vorticity values. The solid black lines in this chart indicate height contours, lines of equal geopotential height. You can see the height contour lines are labeled 534, 540, 546, and 552, and they are typically in units of decameters. The X on the image indicates a vorticity maximum. I don't see, oh yeah, on the bottom right there's one. You may or may not see it on your screen, but they're a vorticity minimum or a very low value. The lowest value of vorticity is represented by the letter N, but the maximum vorticity value is represented by the letter X. Okay, so the red line in this particular chart, vorticity chart, is showing where the vorticity lobes are located. This is the vorticity lobe axis. So anytime you have these tight packing, these vorticity lines, and they're orientated parallel to the solid black height contour lines, that generally indicates you have what's known as a shear vorticity lobe. And again, they're associated with fast-moving pockets of wind within the jet core known as jet maxes. So now that we talked about vorticity, we're going to talk about the other term 3 that we left out. Now we're going to bring that term 3 and just look at the temperature advection effects alone. We're only going to look at term 3 and term 1 in this case. So we're going to evaluate the effect of temperature advection or temperature changes on vertical air motion, and we can utilize any of these 4 charts really to determine temperature changes or temperature advection. My favorite is the 1,000 to 500 millibar thickness analysis, and I'll show you an example of this chart towards the end as well, along with that vorticity chart. In some locations, it's better to use the 1,850 millibar thickness analysis, and this would be in areas where you have shallow, cold, very dense Arctic air. So you have one of those very strong Arctic outbreaks in the winter where temperatures are below 0. You might want to use a 1,850 millibar thickness analysis. Some cases, like for example in the Rocky Mountains out in the city of Denver, where you're sitting at a mile high, 5,000 feet above sea level, you might want to use the 850 millibar thickness, 850 to 500 millibar thickness chart. Mainly because the 850 millibar level is at surface on the ground in a location such as Denver because they're a mile high. The 925 millibar analysis is another good tool to use to evaluate temperature advection or changes. 925 millibars is located about 2,500 feet above the ground. And then 850 millibar analysis is also a really excellent tool to look at temperature changes in the lower troposphere. 850 millibars being 5,000 feet above the ground. So when we look at the 1,000 to 500 millibar thickness chart, that I really love to look at that chart. Tropical Tidbits website has it a lot. It's really a very useful chart. It provides an estimate of the lower tropospheric temperature advection or temperature changes. Is warmer air moving in? Is colder air moving in? That's what we're looking at on the 1,000 to 500 millibar thickness chart. Thickness is directly proportional to temperature. So if I increase my thickness, that means my atmosphere is expanding as I increase my thickness, and that means my temperatures are increasing. So increasing thicknesses in the atmosphere indicate increasing or warming temperatures. Decreasing thicknesses indicate colder temperatures in the atmosphere. So there's a directly proportional relationship between thickness in the atmosphere and the temperatures. And that's why these charts are so useful. Now, in some situations, as I mentioned, during strong outbreaks of polar or Arctic air in the winter, you might want to use a 1,000 millibar to 850 millibar thickness chart. 1,000 millibar is generally considered to be on the Earth's surface where we live. 850 millibars is up at 5,000 feet. So because the Arctic air is more dense, it tends to hug the ground. The atmosphere is more compact. So you may want to look at 1,000 to 850 millibar thickness in that case with Arctic air. The 925 and 850 millibar chart may be used in conjunction with the thickness chart in areas where the surface is near sea level. It's just a little rule of thumb. And the 700 millibar chart may be used as a backup for the thickness chart in mountainous areas. Okay. Why is that again? Because in mountainous areas, 700 millibars is about 10,000 feet. So if you have really tall mountains, your surface may start at 8 to 10,000 feet. Here's a comparison of the 700 millibar chart on the right to the 1,000 to 500 millibar thickness chart over mountains to the left. Notice the pattern is different, right? The solid black lines in both charts indicate lines of equal height. Okay, but notice that you have a dipping over the over the mountains of the desert Southwest with the 1,000 to 500 millibar thickness chart. So you have this lowering of the heights because of the mountains on the left-hand image, but on the right-hand image, if you used a 700 millibar chart, then you don't really see that. So the distortion's gone on the 700 millibar chart at 10,000 feet as compared, because the 1,000 millibar on the left is going to be below the elevation of the mountains. So it's really not going to be very useful. So that's really what I'm trying to point out here. All right, so let's get back now to talking about temperature advection alone. So we're totally disregarding the vorticity advection from the omega equation. We're going to look at cold air advection, which is going to be abbreviated CAA. So cold air advection in the lower troposphere. What happens when we have cold air advection? Right. We're not considering vorticity advection again, so we're comparing the temperature advection, term 3, with the term 1 vertical motion. If you get cold air advection, that is going to lead to downward vertical motion. Okay. Just think about this. During cold air advection, that's the case where you have colder temperatures moving in. The atmosphere is much more dense. Cold air is way more dense than warm air. So that cold air tends to add weight to the air column. That's going to result in the air sinking. So the image, the portion on the left here is showing at the surface we have cold air advection in the lower troposphere at the surface. We're looking at 1,000 to 500 millibar thickness analysis here. So the left-hand portion is what we're focused on right now. Well, we're looking at cold air advection at the gradient level. The gradient level is generally above 3,000 feet, where you don't have there's no more friction involved. The winds are able to blow freely. They're not slowed down in any way. What you have going on in the left-hand portion of the image is you have cold air advection in the lower troposphere. You have a surface cold front represented by the blue solid line there in the bottom left with those blue solid triangles. So you get this cold air advection at above 3,000 feet, right above the surface. You've got all this cold air coming in. You get downward vertical air motion. Okay, the air is so much denser, it wants to sink. So cold air advection in the lower troposphere favors downward vertical motion. Fancy term we use in meteorology to describe downward vertical motion is subsidence. You're going to get surface pressure rises because the air is much heavier and denser. It's going to add more force per unit area. That's going to cause your barometric pressure to rise. Warm air advection, on the other hand, in the lower troposphere, same thing, right near that gradient level, 3,000 feet above the ground, above that level. Friction is no longer a factor. When we have warm air advection, the atmosphere wants to expand. It wants to grow taller. Warm air is it's much less dense than cold air, so the atmosphere expands, the thicknesses increase, and you get upward vertical motion as a result. So the right-hand portion of the image, in this case, we have warm air advection represented by that arrow, okay, at the gradient level, and you have upward vertical motion because the air is less dense. This typically happens on the backside of surface high pressure systems when your winds switch around to the south and southwest in the northern hemisphere. So warm air advection, what's that going to do? It's going to result upward vertical motion of air, ascent, rising air. As air rises, it cools, it condenses, it forms clouds, and surface pressure is also going to fall. As air rises upward away from the Earth's surface, that force per unit area decreases or gets less, and your barometric pressure is going to fall as a result. Warm air is much lighter. If we were to weigh warm air and cold air side by side, that warm air would result in surface pressures much lower than the colder air. All right. So evaluation of terms 2, that vorticity advection, and term 3, temperature advection, combinations on term 1, vertical motion. If we were to combine both the vorticity advection and the temperature advection now, we're going to see we're going to look at a couple different situations. Let's go ahead and take a look. Okay, here's a nice little chart. Possible temperature and vorticity advection combinations. So you have temperature advection, you notice on the left, and then you have vorticity advection at the top, kind of written across horizontally there. So if you have neutral temperature advection, WAA stands for that warm air advection, CAA cold air advection. Okay. And then you combine neutral temperature advection with neutral vorticity advection, you get neither rising or sinking air. If you combine neutral temperature advection with positive vorticity advection, you get upward rising air. If you combine neutral temperature advection, which means there's no change in temperature, and you only have negative vorticity advection, NVA, you have downward vertical motion. So when I say, when I have one of these cases where temperature advection in this case is 0 or neutral, I want you to consider completely disregard it. If it's neutral, it's non-existent. And now you're only focusing, like we just went over, you're only focusing on PVA and NVA, positive or negative vorticity advection. All right. Now what happens if you have warm air advection? I'm in the second row there. If I have WAA, warm air advection, and then I have neutral vorticity advection, I'm going to have upward rising air motion. If I have warm air advection and positive vorticity advection, PVA, I'm also going to have upward vertical motion. But if I have warm air advection and I don't know what the negative, I don't know the vorticity advection, then what's going to happen, right? In this case, we really, we don't know what the overall vertical motion is going to be. And then lastly, the third row, CAA cold air advection. So I have cold air advection, colder air moving into an area, but I have neutral vorticity advection, I have downward motion. But if I have cold air advection and PVA is unknown, then we're not really sure what's going to happen there, whether we're going to have rising or sinking air. And then cold air advection and negative vorticity advection, that combination is going to give me downward vertical motion. So I hope you're kind of getting the handle of things here. I'm combining, we separated them at first. We only looked at temperature advection or temperature changes. Then we moved into vorticity advection and vorticity changes. And now we're combining the two. Here is a much more thorough breakdown with possible temperature and vorticity advection combinations in the atmosphere. I am showing the first two columns, vertical columns, show vorticity advection and temperature advection. Okay. If there's a black like the black area, that represents that temperature advection is non-existent, or vorticity advection is non-existent. So if it's a black block, that means they're not factored into this, right? So I have a lot of combinations of those two rows on the two columns on the left, vorticity advection and temperature advection. And then I have columns for upper heights, surface pressure, vertical motion, stability, clouds, and the adiabatic process. All right, so I will tell you this, that if you have rising upward motion, rising vertical motion, you will have adiabatic cooling. If you have sinking air motion, downward motion vertically, you're going to have adiabatic warming. So that is the way that works. So adiabatic process is dependent on whether the air is rising or sinking. If it's rising, you have adiabatic cooling, because air cools as it rises. And if adiabatic process is warming, that means you have sinking air motion, and sinking air motion results in a warming process. All right. So let's look at a couple of these combinations. I won't do all of them, but just kind of show you the importance of both positive vorticity advection, negative vorticity advection, and then the temperature advection, the warm and cold air advection. This all has to tie in with that classical omega equation we broke down. So if I have just PVA alone, I'm in the very top row. All right, see Vort ADV, vorticity advection is PVA. My temperature advection is the black blank block. So I only have PVA. In this case, my upper heights are going to lower or fall. See, the arrow pointed down means falling. The arrow pointing up means rising. So with PVA alone, no temperature advection, upper heights are going to fall, surface pressure is also going to fall, the vertical motion is going to be upward, the stability is going to fall or decrease, and whenever I have rising air motion, vertical motion, I'm going to get cooling, adiabatic cooling, and I'm going to form clouds. Possible precipitation. Second row, NVA. So I have negative vorticity advection, okay? Negative vorticity advection, but no temperature change, no temperature advection. That's going to cause my upper heights to rise or increase. My surface pressure is also going to rise with just NVA. Vertical motion is going to be downward. I'm going to have sinking air motion with just NVA. My stability is going to increase or go up. And then when you have sinking air motion, that results in adiabatic warming, and that results in decreasing clouds, dissipating clouds. Think of clear skies in this case. The third row shows that I have no vorticity advection, and I do not have temperature advection at all. That's pretty simple. That means there's no change to any of these elements in the atmosphere. The fourth row now shows I don't have any vorticity advection. Okay, so I have cold air advection, CAA, in that fourth row. My upper heights are going to fall because the cold air advection, the cold air is much denser. Surface pressure is going to rise. The vertical motion is going to be sinking or downward. Stability will increase, and I'm going to dissipate or decrease clouds with that case, with cold air advection. I'm going to have air that sinks, which is going to result in adiabatic warming and dissipation of moisture and most likely clear skies. Warm air advection, I'm going to have only warm air advection, no vorticity advection. I'm going to have upper heights increasing because with warm air advection, warm air moving in, my atmosphere wants to expand. Upper heights are going to increase. My surface pressure is going to fall because that warm air is much lighter. It's not going to weigh as much. Barometer is going to fall. The vertical motion is going to be upward. The stability is going to decrease because my air is rising and adiabatic cooling. And my clouds are going to be on the increase with just warm air advection. And then if I don't have any vorticity advection factored in, and I have neutral temperature advection, the sixth row there shows no change again. Now what happens if I have PVA and cold air advection? What's going to happen there? Well, in this case, positive vorticity advection and cold air advection are going to result in a lowering of my upper heights. But I don't have enough information to determine the surface pressure, vertical motion, stability, and clouds, and adiabatic process. I would have to use additional methods to figure out which is more dominant in this case to give me, anywhere where there's question marks here in the bottom rows, that indicates it's unknown. We're not sure. If I have positive vorticity advection PVA plus the warm air advection WAA, what's going to happen to my heights? Well, I don't know, because warm air advection indicates increasing heights, PVA indicates decreasing heights. So they counteract to offset each other. I do know, though, with a combination of those two, PVA and warm air advection, my surface pressure will fall, my vertical motion will be upward, and then my stability will decrease, and my clouds will increase because of adiabatic cooling and rising air motion. Now, NVA, negative vorticity advection, and the CAA, cold air advection, that combination, I don't know what's going to happen to the upper heights again, whether they're going to rise up or get lower, because NVA is going to tell me that my heights want to rise, but cold air advection tells me that the heights are going to fall. So I would need more information. I'd have to determine which is more dominant in this case, the NVA or the CAA, the negative vorticity advection or the cold air advection. But I could determine the surface pressure, the vertical motion, stability, clouds, and the adiabatic process. In this case, with NVA, negative vorticity advection, and cold air advection, I do know my surface pressure increases when I combine those two. I do know the vertical motion is downward when I combine those two. I do know the stability increases, and with downward vertical motion, you have a drying and a warming of the parcel, which is going to dissipate the moisture and decrease the clouds via adiabatic warming. And then NVA and warm air advection at the very bottom. I do know that both NVA and warm air advection, negative vorticity advection and warm air advection, are going to result in upper height increases. But I do not know, I don't have enough information by just looking at this chart to tell me which is the more dominant of the two. That's going to help me determine where all those question marks are at. Surface pressure, vertical motion, stability, clouds, and adiabatic process. That'll help me fill those question marks in with some answers if I have more information. All right, so here we are. We're looking at the combination. We kind of got ahead of ourselves with this chart. But now we're going to break it down. We're combining vorticity advection and the temperature advection. So if I have positive vorticity advection and warm air advection, my term one, my VM vertical motion is upward. If I have negative vorticity advection and warm air advection, I'm combining those two. I'm going to vertical motion. NVA indicates downward vertical motion. Warm air advection indicates up. So you see the last row here of this slide. VM is equal to down plus up equal question mark. Because again, in this case, NVA brings my height down. Warm air advection brings my heights up. So I'm not sure. I'd have to examine this further to determine the vertical motion. If I have positive vorticity advection, PVA, and CAA, cold air advection, positive vorticity advection is going to indicate upward vertical motion. Cold air advection, however, is going to indicate downward vertical motion. So again, these two offset each other. PVA and cold air advection offset each other, counteract each other. So I'd have to know more information. I have to figure out which is more dominant, that PVA or that cold air advection. If I have NVA and cold air advection at the same time in the atmosphere, I have NVA, which indicates downward vertical motion. I have cold air advection, which indicates downward vertical motion, and that's going to result in downward vertical motion. So this is a no-brainer. Those are your combinations you can get. All right, and that's all on this chart. It breaks everything down nicely. All right, we look at vorticity advection and temperature advection, PVA and warm air advection at the same time, upward vertical motion, NVA and warm air advection, unsure, we need more information. PVA, positive vorticity advection, cold air advection, unsure, we need more information. And then NVA and cold air advection both indicate downward vertical motion in the atmosphere. Now let's get to the final piece of the training tonight. Let me show you some example charts. So these are vertical velocity charts at 700 millibars. 700 millibars in the atmosphere is about 10,000 feet above the ground level. These charts are in microbars per second. The image on the left, the graph on the left, that little chart on the left, the pink, magenta, and blue shading, the purple colors, they indicate upward vertical motion. There's a little scale at the bottom there on the chart on the left that shows your values of vertical motion, or vertical velocity. Vertical velocity is in microbars per second. So the pink, magenta, blue, that purple shading indicates where there's upward vertical motion. This chart was taken back in December of '96. There's a good chance we had rising air motion in the purple shading, most likely out ahead of a cold front. It looks like it's a shape of a cold front as it's moving through the Midwest. The image on the right, the chart on the right, shows another type of vertical velocity chart at 700 millibars or 10,000 feet. The reddish colors and the yellow colors indicate upward vertical motion. All right, so you see yellow and reds, that's upward vertical motion. If you see purples, that's downward vertical motion. If you see blues, that's downward vertical motion. So this is an example of a vertical velocity chart. And again, the vertical velocity is not all that great in magnitude, but it's very important. It doesn't take much rising or sinking air motion to really affect the sensible weather at the surface. Here's an example of the thickness charts. And again, we would use thickness charts to determine whether we had cold or warm air advection, changes in temperatures in the horizontal. The image on the left, the chart on the left, is an example of a cold air advection. I put the letter CAA in there for short. You have an area of low pressure. This is, I'm looking at the time of year here, this is early January of 2018. This happened to be a very good little storm system for southeast Virginia and up the mid-Atlantic. This surface low actually dumped snow on Charleston, South Carolina, all the way down to the coastal Georgia before moving up the East Coast and really becoming a bomb cyclone. But there was a very strong push of cold air behind this very strong low pressure system off the southeast coast. The green dashed lines on the image on the left, they're showing, basically they're showing lines, the thickness lines. The red thickness line indicates the rain snow line, the 540 decameter thickness. Just showing the solid black lines indicates lines of equal surface barometric pressure. They're isobars, lines of equal barometric pressure at the surface. And whenever the black lines intersect those green dashed lines or cut across at an angle, that indicates some sort of advection. In this case, it's cold air advection. The winds shift around to the north and the northwest on the backside of this low pressure system, which is situated off the coast of the Carolinas. The image on the right, the graph on the right, the chart shows warm air advection. We have a surface high at 1034 millibars situated on the image, the graph on the right, chart on the right, at 1034 millibars over northeastern Pennsylvania. The wind flow in the northern hemisphere around high pressure systems is clockwise. Those solid black lines are cutting across those red dashed thickness lines. So you have some sort of changes in thickness, some sort of temperature advection. And on the backside of high pressure systems in the northern hemisphere, you typically get south and southwest winds, which indicates warmer air advection. Vorticity charts. This is the last chart I'm going to talk about tonight. The chart on the left, there's a scale there on the bottom portion of the chart on the left. You see the different values. You see a negative 4.0, and then it goes 4, 8, 12, 16, 20, 24, all the way up to 40. All right, so on the vorticity chart, the positive vorticity advection, the PVA, indicates upward vertical motion, and that is represented by the red and the pink colors here on this particular chart on the left. So you see the pink maroonish colors, then yellow, then greens. That indicates the positive values on that scale on the bottom right of vorticity, which indicates PVA and upward vertical motion. So there's some sort of lifting going on. There's a surface low pressure system in the lee of the Rockies in this case, and most likely you have a lot of clouds and precipitation just to the east of the Rockies. And then that little image on the right shows vorticity in the upper troposphere. You generally have negative vorticity advection, as we already talked about, NVA, and that generally occurs downstream from the ridge axis. And then you have positive vorticity advection, PVA, which occurs just downstream from a trough axis. So on the wavy pattern here, if we're looking at a short wave at about 500 millibars, 18,000 feet in the atmosphere, your lowest vorticity values, the vorticity minimums, would be at the ridges, at the main ridge points, and your vorticity maximums, or cyclonic turning of an air parcel, would occur in the troughs. Negative vorticity basically means that a parcel of air is negative vorticity is spinning. It's when the parcel is spinning anticyclonically or clockwise, indicate downward vertical motion. Whereas positive vorticity advection, the air parcel is spinning cyclonically or counterclockwise, indicating upward vertical motion. But I wanted to show you an example of a short wave. So generally you have PVA on a short wave out ahead of the trough axis and negative vorticity advection basically behind the shortwave trough axis. All right, that wraps things up tonight on the training. We covered a lot of great material. We learned a lot about, we looked at the omega equation. We broke down the classical omega equation. We looked at two main factors we need to consider when determining vertical motion in the atmosphere: positive vorticity advection, negative vorticity advection. So we looked at the vorticity advection aspect. We looked at the temperature advection aspect, where you have CAA, cold air advection, colder air moving into an area, or WAA, warm air advection, with warmer air moving into an area. And these are very important parameters. We need to look at, when I'm looking at a forecast, I'm looking at, vertical velocity is very important to determine if my air is rising or sinking. I'm also looking at the thickness charts here to determine whether I have colder air advection, CAA, or WAA, warm air advection. Because remember, cold air advection indicates downward vertical motion, warm air advection indicates upward vertical motion, right? And then vorticity charts, just as important. I'm looking at 500 millibar or 700 millibar charts, weather charts, 18,000 feet to 10,000 feet. I'm looking for these little short waves, and the positive vorticity advection being out ahead of the shortwave trough axis, and the negative vorticity advection being behind the shortwave trough axis, with PVA indicating upward vertical motion and negative vorticity advection, NVA, indicating downward vertical motion. When you combine the effects, when you have warm air advection and positive vorticity advection ahead of a shortwave trough axis, then you're in business for a lot of rising air motion, clouds, and a storm. Precipitation, most likely. On the other hand, if you have negative vorticity advection and cold air advection behind that shortwave trough axis, you're most likely getting downward vertical motion, drying air mass, and surface high pressure most likely is moving in. This type of stuff is really valuable on the synoptic scale when we look at major storm systems, mid-latitude storm systems in the wintertime especially. There's a very distinct pattern that takes place as these short waves propagate through the long wave pattern, getting blown through by the jet stream winds and resulting in upward vertical motion and downward vertical motion. And it's a very useful pattern to get down in your mind as far as forecasting goes. All right, that wraps things up tonight. Spot on weather. Appreciate you listening in. A very interesting topic tonight. This is really a great portion of dynamics in the upper levels of the atmosphere, what goes on. Thanks for watching, and most importantly, thank you for viewing the video. Take care, everybody. A lot more to cover. We got tropical weather training soon to follow, so appreciate everybody's support for Spot on Weather on YouTube. Continue to follow us on Facebook as well as Twitter with the daily forecasts. I share a lot of interesting tidbits. That wraps things up. Spot on weather. If we're not spot on, we're not doing it right. I hope you enjoyed the training, everybody. Have a great night, and try to stay cool right now in this heat wave.